Hi everybody and welcome. In this video tutorial I would like to give a complete example of a Bayesian analysis. So to start with, we're going to remind what the Bayes theorem is and why this is useful. So Bayes' formula simply says that the probability of A given B is the probability of B given A times the probability of A divided by the probability of B. So A and B are two events here, and what is interesting in this formula is that the positions of A and B on the left-hand side and on the right-hand side have been swapped. So this here on the left-hand side is called the posterior distribution, and on the right-hand side, that particular distribution that is here is called the prior distribution. So what's interesting about this specific formula is that when we have a certain belief or a certain probability of occurrence of the event A before anything happens, we can write it as P of A. Once the event B has happened, we are interested in the probability of A. So in a sense, this is an update formula. In the beginning, our knowledge or our belief about the event A were encapsulated by this term here, P of A, the probability of A. And after the event B has happened, has been observed, then our new belief, the new probability of the event A is this one. So this is a formula that tells you how to update your belief about the probability of A after the event B has been observed. And so the other terms of this formula are quite important as well. They say that to do this, you need to be able to compute the probability that B would happen if A is indeed the case. And critically, you need to compute the overall probability of B. What is the chance that B would occur irrespective of the event A? So that here really summarizes the whole Bayesian analysis. In general, we are interested in computing the posterior distribution, and computing the posterior distribution really corresponds to a fully Bayesian analysis. So we're going to give an example now using the Gaussian distribution to show how this can be useful. So let us give a quick reminder about the Gaussian distribution. The Gaussian distribution is the bell curve. It has a probability density function that looks something like this, which is a typical bell curve. And it has two characteristic parameters that are informative about the particular shape of the distribution. The first here is often denoted mu, and this is the expected value, or also the mode, the central value here of the distribution. So here, this is the parameter mu, which is the central value, and it has another interesting property, which is the spread here, how wide, how flattened the curve is. And this is usually represented by a parameter which is written sigma, and I'm going to write it sigma squared, which is to specify that this is the variance. So I'm going to write the variance as sigma squared, and to specify that sigma is the standard deviation. So when the standard deviation is high, the curve becomes much flatter. So it doesn't change anything about the central position. It would remain where it is at mu, but we'd get something that is much flatter like this when the standard deviation is high. So a typical case here where the standard deviation increase would look like that. So in that particular case, we would have a sigma squared, which is higher on the right hand side than on the left hand side. So that here is the overall shape of the Gaussian distribution. And it is important to know the specific formula that links the parameters here, mu sigma squared, with that particular curve here. And that formula, one has to know it, is given by the probability density function, which we write f of x. So that gives in a sense, the probability of the event x, even though this is not really a probability because the event x is continuous. So we can only give the density of probability here. And the specific expression is that this is 1 over sigma square root of 2 pi times the exponential here of minus 1/2 x minus mu divided by sigma everything squared. And so here this is an exponential of something in x squared. And what's interesting is that within these brackets here, we can see that x minus mu divided by sigma is the centered and reduced or standardized expression for x. So this is a term here which has expected value 0 because we have removed mu here, and that has standard deviation or variance equal to 1. So that here is the expression for the Gaussian distribution. With that, we are now ready to consider a particular case of Bayesian analysis. We are going to consider the case where the parameter mu itself is a random variable. So this is fairly typical in Bayesian analyses, is that x here, of course, is a random variable because it has a Gaussian distribution. But we are going to consider the case that we do not know what mu is, and more than this, mu is going to be random, which means that whenever we run an experiment, a statistical experiment, then mu may have a different value. And we're going to further assume that mu has a Gaussian distribution. So if x here has this distribution, we say, or we write down, that the variable capital X, x stands for a specific, small x stands for a specific value, and capital X here stands for the name of the variable. And we say that x here has a normal or Gaussian distribution with parameters that are mu and sigma squared. That here is equivalent when I say that x has a normal distribution or Gaussian distribution with parameter mu and sigma squared. I mean that the density of probability is this one here. So we are now going to consider a case where mu itself has a Gaussian distribution. So we're going to say that first we draw mu from a Gaussian distribution. So it must have two parameters, and we're going to use the parameter a for the expected value of mu and the parameter b, and then specifying square to say that this is here the variance is b squared and the standard deviation is b. So we say that first we draw mu from a normal or Gaussian distribution, and the parameter of this distribution are a and b, which are known, but mu is unknown because mu is random. And when this is done, then we're going to say that x will have a Gaussian distribution of which the expected value is mu and of which the standard deviation is sigma, which is a known value. So we're going to say that we have no doubt about the value of sigma, but mu itself is a random variable. So mu cannot be known because it has some variation, some random variation. All we know about mu is that it has an expected value of a, which is known, and a standard deviation of b, which is also known. But the value of mu, we do not know. And so now it becomes interesting that we're going to observe the variable x here. And so it means that these values will be known, but we are never going to observe the variable mu. Mu is a parameter we'd like to estimate, and we first assume that here it has this distribution, but after we observe the values of x, we're going to change our mind to update our knowledge about the distribution of mu. So we are going to observe here n times the variable x. So we're going to get an observed sample of x1 to xn, and this here will have this distribution, except that mu is not known, and mu, we are not going to observe it. And so if we now go back to the base formula, which is here above, then what we're interested in is to know how we can compute the probability of mu here given the observations. So once we have observed the x, the term looks like this. So we are interested in knowing what is the distribution of mu after we have observed the x that are here, and we can use the base formula here to say that for this we need to compute the probability of the x1 to xn given mu. We also need to compute here the probability of mu, and finally we need to compute the probability of the xn from x1 here to xn. So some of the terms are already known. Probability of mu, we know it. This is here. We know that mu has this distribution here, which is the Gaussian or normal distribution with parameters a and b. This is the prior distribution of mu. Here, this term is called the likelihood, and that is what we say here, is that given the particular value of mu, the x1 to xn have got that distribution. They're Gaussian as well. The term that we're looking for is this one, so that's what we want to compute. But there's one term that we do not know, and this is the denominator. This one here, we don't know what that is. And what we're going to do right now is to compute that term, or more specifically to compute the entire term that is here on the right hand side, so that we know what is the posterior distribution of mu once we have observed the variables x1 to xn. So the first thing that we're going to do to compute this is we're going to focus on the numerator here. We're going to find a specific expression for that numerator, and we're going to use the definitions that we have. So the first is that we have here the expression for the x given mu, and so because this is a Gaussian distribution, we can write it specifically. And also we're going to assume that the x1 to xn have been sampled independently, which means that this distribution here is the product of their probability density function. So we say that the numerator is equal to the product with I equals 1 to n of the standard deviation here sigma. We have the square root of 2 pi term that is here, times the exponential of minus 1/2, and we have then x minus mu, which is here, and here this is xi divided by sigma everything squared. So we have n terms in the product here times the probability density of mu is 1 divided by the standard deviation of mu is b, and then we have the square root 2 pi term as usual times the exponential of minus 1/2, and this time mu is the variable and the parameters are a here and b that are here. And this is it. So we have a product here of exponentials. And this is the numerator of that particular expression here. So just to make it clear, I'm going to say that this is just the numerator. It goes here. The denominator, we're not going to compute it. What we're going to do instead is to find another expression for this numerator where we will see that mu has a Gaussian distribution. And once we have observed that this has a Gaussian distribution, we will not need to compute the denominator. We will just need to know the two parameters of the new Gaussian distribution here that mu follows once x1 to xn have been observed. So what we're going to observe here is that because this is a product of exponential, the terms that are inside the exponential are going to add up. And so this here is equal to a certain constant that I'm going to write c, because I don't really care what this is. I just know that this does not depend on mu. This is all I mean by c here. So it's going to be c times the exponential of minus 1/2, and then I'm opening a large square bracket of all these terms that are here, except that this was a product before, and now this is going to be a sum. And what I'm going to do is I'm going to put the terms here that are on the right hand side, I'm going to put them on the left first. So the very first term is the one that we had here on the right, and that is mu minus a divided by b, everything squared. So that's the first term here. And the other terms that we have, they're of this form that is here. So that's x1 minus mu divided by sigma, everything squared. And we have n of those terms. So I'm just writing the first and the last. So the last is xn minus mu divided by sigma, everything squared. So that's what's inside the exponential here. So we have this global term that shows basically where the parameter mu appears. So remember that mu is the value that we're kind of after. We have observed x1, xn, etc. These are things that we know. We also know sigma, and we know a and b. A and b are the hyperparameters. They are the parameters of the distribution of mu before we had any information regarding x1 to xn. So we now have to represent this particular expression in a way that makes sense and that will allow us to guess what is the distribution of mu given x1 to xn. So this is just a very basic algebra here, where we have to know a little bit how to manipulate expressions of squares. And this is a little bit tedious, but this is not particularly difficult. So what we need to do now is to expand this and to gather the terms in mu and see what comes out. So what I'm going to do is to focus only on these terms between square brackets that is here. That's all I need to focus on for now. So here we go. I'm just going to focus on the terms between square brackets. And so I'm expanding this, and I obtain mu squared here minus 2 times a times mu and plus b squared plus a squared here, and everything is divided by b squared. That's the first term. The second term that we get here is going to be quite similarly. I'm going to put the mu first here, and so that's mu squared minus 2 times x1 times mu plus x1 squared, and everything divided by sigma squared. I don't need to write the other terms here. They're similar to the first. So here we have one first term which is slightly different from the others. And after this, we have n terms that follow this pattern here, that are like this. If now we want to gather the terms in mu squared, we have the little difficulty that the denominators here are not the same. So we need to bring everything to the same denominator. So what we're going to do is to work a little bit on that side here and re-express this so that we have a denominator which is sigma squared. So we get something here which is going to be over a sigma squared this time. And to obtain this, what I need to do is to say that I have mu squared here times sigma squared divided by b squared. So when I express things this way, then this allows me to put everything over sigma squared. And the other terms, they look quite similar. So this is minus 2a mu. And again, I have this term here that appears, sigma squared divided by b squared. It's getting a little packed here. And the last term is, once again, a squared times sigma squared divided by b squared. And so now I have everything over the same denominator here. And here I don't need to do anything. So I'm just going to let you replace the dot 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 by the terms that are here. And I am now able to gather the terms in mu squared. So here we go. So we have everything over sigma squared now, and we start collecting and gathering the terms. So mu squared, I have in that first term sigma squared divided by b squared. And I have n terms like this. And how many times do I have mu squared? Well, one each. So here, this gives me n. Okay, I have collected this term here and all the terms, all the n terms that were here. So that's it for the mu squared. Now we're further collecting the mu terms. And so we get minus 2, 2 is present every time, times mu, and then we collect the rest. So what do we have? Here we have a times sigma squared divided by b squared, sigma squared here divided by b squared. So that's what we have here on that very first term. What about the others? I have x1, x2, etc. until xn. So plus x1, etc. until xn. So that's what I have here for the mu terms. Okay, I have taken this term here, so minus 2 mu times a sigma squared divided by b squared, and I have taken these terms that are here, minus 2x1, minus 2x2, etc. until xn, that is here. And so what about the rest? Well, the rest I don't really care. So what I'm going to say is that I'm going to bring this here over sigma squared, like it is, and I'm going to say that there is a constant here that I'm just going to write as C, and I'm going to use very liberal here notation because C is not the same as the one we had before. It's just to say that this is a constant, and by a constant I mean something that does not depend on mu. Okay, and this term here is not really relevant for me. It is there, so I still keep it as a constant, but it's not really important for me. So I just say that this is a constant here, and we're going to work with this. It's going to simplify the calculations a lot. So if you just go along with the idea that all the terms that do not depend on mu, we collect them together into a single value that we call C all the time. So we're making progress here, and what is interesting is that we would like to express this here into a different form, but we have the difficulty that there is this term here, which bothers us. So we're going to take it out of this ratio here, and so that we have just something that has mu squared in the beginning. So here we go. We take it out completely, so we get something that says sigma squared divided by b squared plus n. Okay, I've taken it out, and then we say divided by sigma squared. This is the sigma squared that is here, and now we have mu squared here minus 2 times mu, and this term here, I need to divide it by that, which I have taken out of the ratio. So that's going to be a new ratio that I write. So A times sigma squared divided by b squared plus x1 plus all the terms including xn, and dividing everything here by that term that I've put in factor here. So it's going to be sigma squared divided by b squared plus n, like that. And so that here is of course within these brackets like this. And as usual, everything else still does not depend on mu, so I'm just writing it as a C to say that this is a constant that does not depend on mu. So I now have this expression here, which I remind you is what is between these square brackets that are here and that are themselves within an exponential. And the reason why I'm writing it this way is because I would like to express this as a square. And I'm getting close to that here because I'm almost done. As we're going to see now, this I can re-express as sigma squared divided by b squared, nothing changes here, plus n divided by sigma squared. And this term here, I can say that this is also, this can be expressed as mu minus that term that is here. So here we go, we write it. A sigma squared divided by b squared plus the terms here, x1 to xn, and the denominator doesn't change. Here is the same. So I can write it like this and square the whole thing here. So as you can see, if I now expand this, it will be mu squared, which is there, minus 2 times mu times this, which is this term, plus that whole thing to the square. And that's, again, something that does not depend on mu, so I can just pack it into my term c here, which I abuse all the time. So I now have a new expression, which is quite handy, and that says that I can re-express the numerator of base formula as a function of this here. So I am now ready to express again the numerator completely now with this writing. So let's scroll back to what we had in the beginning. We had that this is a certain constant times the exponential of minus 1/2 of all this. Like, this is the numerator, and now I'm going to re-express this in one final form. So the numerator will be equal to a certain constant times the exponential minus 1/2 times this here, which is between square brackets. And so here we go again. We write it one more time. Sigma squared divided by p squared plus n. Here divided by sigma squared. And then times mu minus this big term here. So a times sigma squared divided by b squared plus vxi here, and divided by this denominator here, sigma squared divided by b squared plus n. So I close this here, and what's interesting is that I don't need to say plus c here. Okay, why is that? Because exponential of a constant, this is a multiplicative constant. So I finally have found that the numerator of the base formula is equal to a constant times this here. Okay, and so just to remind exactly what that is, this is here the probability. So I'm going to use F to remind us that this is a density of probability. So that's the F of mu times F of x1 till xn given mu divided by F of x1 till xn. And so that here is also equal to the density of probability, the posterior density of mu given dxi. So given x1 till xn. And so it's important to observe that here, this is a density, a probability density function. So the integral, the sum of it, has to be equal to 1 because this is a probability. And so in that sense, the denominator here is a constant. As you can see here, it does not have any mu involved in it. So this is just a constant, which allows the numerator to sum out to 1 or to integrate to 1. So this constant that is here can be anything such that the integral here with respect to mu is equal to 1. But when we look very carefully here at this expression, we see that this looks very much like a Gaussian probability density function. So what we find here is that this is here, I forgot the square term, which was here all the time. So that we have here a term where mu has expected value, this thing here, and has variance, which is sigma squared divided by sigma squared divided by b squared plus n. So now what we find is that the distribution of mu given the x1 etc. till xn is a Gaussian distribution here, and the expected value is this term which is there. So that's a here sigma squared divided by b squared plus x1 plus all the term till xn here divided by this here, so sigma squared divided by b squared plus n. So that is the expected value, and the variance is given here, but of course this is usually divided by sigma squared, so now we have to invert it again. So that is sigma squared divided by sigma squared over b squared plus n. And so here, this is the final conclusion, that after we have observed the x1 to xn, the distribution of mu is still Gaussian, but the expected value here has changed. It was initially a when we had just the prior distribution here. It used to be just a, and now this is a very much updated term which looks like this, and the standard deviation used to be b, and now again this is a very much updated term which looks like that. And so what's interesting as well is to see that we can now look what happens in particular examples when we have a case where, going back to the idea that we have x here is distributed like a Gaussian with parameter mu, which is unknown, and parameter sigma, which is known here. And if we observe x1 etc. until xn, we could say because mu is the expected value of x, what is the naive estimator of mu when we don't have a Bayesian approach? Well, this would be just the average. So this is something that is written sometimes here between these brackets. Mu, that stands for the estimator of mu. This is a notation that comes from physics. And so when you have something like this, it would say that this is x1 plus all the terms till xn divided by n. That would be the naive estimator. And you can see that our less naive estimator here has a different expression. It has this sum of the x1 to xn. It has the n terms here, so it looks a little bit like this term here, but it has some coefficients that are here. And so in reality, this term here is a weighted sum of, on the one hand, the observations, x1 to xn, and on the other hand, A, which was the initial belief that we had regarding the distribution of mu. So this initial belief here, the weight of this initial belief is represented with the terms that are in pale blue here, to say that the difference between the naive estimation of the standard approach, of the non-Bayesian approach versus the Bayesian approach, is that there are some residual of information here, A and B, that come from the initial belief about mu that come into the estimator. We also see that this parameter mu here has an uncertainty. So this here represents the remaining uncertainty about the position of mu. So this is something that depends on sigma, which is the spread of the x themselves. And as n increases, as the number of observation increases, you can see that the standard deviation, or the variance here, decreases eventually to 0. But we also have some residual information here in this b squared term that comes from the initial belief that we had about mu. So that example here is interesting with the Gaussian distribution because it's not trivial. It's particularly tedious to go through these derivations, but it's possible. So this is one case where we can know the exact Bayesian posterior distribution, and that will be very useful to benchmark the different methods that we have to do this kind of approaches. So that's it for today. Thank you for listening, and see you soon.